There is an analogy between quantities in rotational and translational dynamics. Complete Table 1, stating in words the quantities in rotational dynamics that are analogous to force and mass in translational dynamics. We've got a table here with translational dynamics and two quantities that follow along with that, force and mass, and then we've got a column with rotational dynamics. Now the first thing to include for force would be torque. If you look at the equation associated with Newton's second law, F equals ma, force equals mass times acceleration, the rotational equivalent of that would be torque is equal to moment of inertia multiplied by angular acceleration. So that will also help us with the second row, but torque for the first row. And as I said before, the rotational equivalent of mass would be moment of inertia, which is a bit like angular mass, but it's also dependent on the radius at which that mass is from the center of rotation. So moment of inertia. Now you'll get a mark for each of those points, so 2 marks. Figure 1 shows a side view of the jib of a tower crane. The load is supported by a trolley which can move along the jib. The jib consists of all the parts of the crane above the bearing, but excluding the trolley and load. We've got figure 1 here with a crane, as stated, with a 35-meter distance between the axis of rotation and the load, and the jib is the horizontal bit that's holding that trolley with the load. The moment of inertia of the jib about the axis of rotation is 2.6 times 10 to the 7 kilogram meters squared. The mass of trolley and load is 2.2 times 10 to the 3 kilograms. The load is at a distance of 35 meters from the axis of rotation. Show that the total moment of inertia of the jib and the trolley and load about the axis of rotation is about 3 times 10 to the 7 kilogram meters squared. Now there are a combination of moments of inertia here. The first thing we need to do is add the moment of inertia of the jib. Now I put IL as the moment of inertia of the trolley and load. And the way that we calculate the moment of inertia of what can be considered as a point mass rotating around an axis of rotation is going to be mr squared, where m is the mass and r is the radius from the axis of rotation. So we know that the radius is going to be 35 meters and the mass is going to be 2.2 times 10 to the 3 kilograms because those are given in the question. So we just need to substitute those values and make the calculation. And that will give us a value of 2.9 times 10 to the 7 kilogram meters squared. Now we don't need to include the unit because that's already given to us in the question, but you can see that 2.9 times 10 to the 7 rounds to 3 times 10 to the 7, so it's approximately that answer. Now this is a 1 mark question, so the mark obtained here will be for the working and the answer together. Figure 2 shows the variation of angular speed of the jib as it turns through an angle of 4.7 radians, or 270 degrees, in a total time of 95 seconds. The trolley and load remain at a distance of 35 meters from the axis. We've got figure 2 there with angular speed in radians per second on the y-axis and time on the x-axis, and we need to find that value of omega max. Calculate the maximum angular speed, omega max, of the jib. Now bear in mind with this graph, the area underneath the graph represents the total angular displacement, which as we've read in the question was 4.7 radians. Now that's going to be equal to the area of all of those 3 shapes added together. So let's substitute this into an equation. So we've got the area of the first triangle, the area of the middle rectangle, and the area of the last triangle. If we take omega max out of all 3 of those and rearrange to make omega max the subject, we can then calculate this value. So we end up with 0.082 radians per second. Now the first mark for this question will be for correctly identifying that you need to find the area underneath the graph, and the second mark will be for correctly calculating 0.082 radians per second. So 2 marks there. At time x in figure 2, the motor that is driving the jib is disengaged. A constant braking torque is then applied to bring the jib to a standstill from its maximum angular speed. The crane driver repeats the movement of the jib with the same load at 35 meters from the axis of rotation. Up to time x, the motion is the same as before. From time x, the trolley is driven at a steady speed away from the axis as the jib continues to rotate until the jib comes to a standstill. Assume the braking torque remains the same as before. Discuss how the motion of the trolley affects the time taken for the jib to come to a standstill. Now let's just go back to figure 2 to see what's happening at time x. So we can see in figure 2 here we've got point x, and that's the point where it's disengaged. So this is the original pattern of motion, but this time the load is being moved away from the axis of rotation. So let's first of all write down the equation that links torque to moment of inertia and angular acceleration. And we can add some labels. Now you'll notice in this question they say that the torque remains constant. However, the quantity that is changing is going to be the moment of inertia because the load is moving away from the axis of rotation. And remember that moment of inertia was equal to mr squared. So making that point will get you your first mark. Your second mark would be for going into more detail on the torque, moment of inertia, angular acceleration equation. So the fact that we're keeping torque constant means that a higher moment of inertia will mean a lower angular acceleration or deceleration in this case. So mentioning that the angular acceleration decreases with a constant torque will get you your second mark. Always good to reference the equation there. And your third mark will be for mentioning that because the angular deceleration is lower, the crane will take a longer time to stop. And that will be your third mark. It's worth just mentioning for the second point that we're actually dealing with angular deceleration, just to avoid confusion. So a mark for each of those 3 points made, 3 marks there. Figure 3 shows the basic principle of operation of a hand-operated salad spinner used to dry washed salads. So we've got figure 3 there with a diagram of the salad spinner. You can see there's a 6 Newton force label. It's a plan view, so it's top down. And then we've got a side view in section, kind of a cross-section view of that container where the salad is placed. The salad is placed in the basket and the lid is attached. When handle A is turned, the basket and its contents spin rapidly. Water on the salad is driven through holes in the basket into the stationary water collecting bowl. The pivot for gear B is fixed to the lid. This pivot and the lid do not move. When gear B rotates, gear C also rotates, but at a greater angular speed. Gear C is fixed to the basket and rotates it. A force of 6 newtons is applied to handle A as shown. Handle A is at a radius of 36 millimeters from its center of rotation. Calculate the input torque. So the values given to us in this question were that there was a force of 6 newtons applied and it was at a radius of 36 millimeters. So converting that 36 millimeters into meters, we have 0.036 meters. Now to calculate torque, we just need to multiply the force by that radius, and that gives us a value of 0.22 Newton meters. I'll just add some labels there. So you get 1 mark for correctly calculating that answer. Gear C rotates 4 times for every 1 revolution of gear B. Deduce whether it's possible for the torque on gear C to be greater than 1/4 of the input torque. Now for this question, we need to obey the conservation of energy, which tells us that energy cannot increase or decrease. But here we're going to say that the power doesn't change. And that will give you your first mark. The second mark would be for including the power equation relating torque to angular velocity and applying that to the situation. So I'll just add some labels there. Now, since gear C rotates 4 times for every 1 revolution of gear B, we're saying that the angular speed multiplies by 4. Now, keeping the power constant, if we multiply the angular speed by 4, we also have to divide the torque by 4. Now, because of that constant power, we're saying that the torque cannot be greater than this quarter. And that would get you your second mark. So 2 marks there. It takes 2.1 seconds for the empty basket to reach an angular speed of 76 radians per second. The torque on gear C is a constant 0.054 Newton meters during this time. Frictional losses are negligible. Calculate the moment of inertia of the basket about its axis of rotation. As we would expect with linear acceleration, being the change in velocity divided by time, the angular acceleration is equal to the change in angular velocity divided by time. So let's write that down first of all, and add some labels. Now making the substitutions from the start of the question, we can divide 76 by 2.1 to find the angular acceleration. And we end up with 36.2 radians per second squared. What we then need to do is apply the angular equivalent of Newton's second law. where torque is equal to moment of inertia times angular acceleration, in the same way that linear force would be equal to mass times linear acceleration. Let's just add some labels there. Let's rearrange this equation to make I the subject and put in the values. And that gives us a value of 1.5 times 10 to the minus 3. And we can write that in the answer space. Now, in terms of marks for this question, you'll get your first mark for correctly calculating the angular acceleration, and your second mark for correctly calculating the moment of inertia. So 2 marks there. The gears are made from polymer or plastic. An early version of this salad spinner suffered from damaged gear teeth. Explain, with reference to angular impulse, why a great force is put on the gear teeth if the user tries to stop the loaded basket too quickly using the handle. So let's first of all write down the equation that we would use involving angular impulse. So I've said there that it's equal to the torque multiplied by the change in time, in the same way that linear impulse is equal to the force times the change in time. So let's just label the torque and the time there. It's worth just stating also that this is equal to the change in angular momentum. So when we're rotating this at a given speed or a given angular momentum, we need to remove all of that angular momentum over a given period of time. So if we have a short time period where that takes place, for a constant angular momentum, then we're going to get a high torque. So the first 2 marks will be for making these 2 points. So the last thing to say is that where the torque is equal to the force applied multiplied by the radius at which that force is applied, if we're keeping the radius constant, then a high torque will also mean a high force. And making this point in sufficient detail and talking about the force exerted on the gear teeth as well will give you your 3rd mark. So 3 marks there. Figure 4 shows a gas strut supporting the lid of a trailer. We've got figure 4 there with the trailer, and you can see that gas strut is labelled with the cylinder. A fixed mass of nitrogen gas is sealed into the cylinder of the strut. The gas is initially at a pressure of 1.2 times 10 to the 6 pascals, a volume of 9 times 10 to the minus 5 meters cubed, and a temperature of 290 Kelvin. When the lid is closed quickly, the gas is compressed rapidly to a final volume of 6.8 times 10 to the power of minus 5 meters cubed. Calculate the pressure and temperature of the gas at the end of the compression, assuming the compression to be an adiabatic process. And the adiabatic index, gamma, for nitrogen is 1.4. So the first thing that we want to do here is write down the necessary equation. Now we've got the product of P and V to the power of 1.4 in each case, before and after. You'll notice that that adiabatic index of 1.4 is the power that we put onto the volume. So let's just add some labels. The first thing that we need to do is use this formula to calculate the pressure. So let's rearrange to make P2 the subject. And then it's just a case of substituting in the values. And that gives us a value of 1.8 times 10 to the power of 6 pascals, which we can write into the answer space. Your first 2 marks will be for making that calculation and getting the correct answer. We then need to use that pressure in the ideal gas equation. You'll notice earlier in the question that it said that this is a fixed mass of nitrogen gas. It's phrases like these that lead us to believe that we need to use some kind of ideal gas equation, because a fixed mass means that we have a constant number of moles. So writing that equation down with a few extra labels. Since N and R are constants, because remember it's a fixed mass, we can say that the value of PV over T is a constant also. Now in this case, we can write down a similar equation to the one that we wrote at the start with P1s, V1s, P2s and V2s. And then it's just a case of rearranging that equation to make T2 the subject and substituting in the values, one of which we've calculated in the first part of the question. So including all of those values, now I realise that's a little bit cramped there, but that will give us our answer to then put into the temperature answer space. So that value should be 328 Kelvin. Now, similar to what we had before, you'll get 1 mark for correctly doing that calculation with the correctly rearranged equation, and another mark for correctly calculating the temperature at the end. I've added on a 1 and a 2 just to show the 2 steps of this question and where the marks are allocated, the first 2 marks being for section 1 and the 3rd and 4th mark being allocated in section 2. So 4 marks there. Explain why the rapid compression of the gas can be assumed to be an adiabatic process. Now, the definition of an adiabatic process means that there is no heat transfer. and that's going to be our first mark. The second thing to say is that if this process takes place over a short period of time, it's very quick, then there won't be any time for any heat to be transferred, so we could consider it to be adiabatic. You could also add in an extra point to say that we can therefore consider the process to be adiabatic, but what I've written here is sufficient. So 2 points made there, 2 marks. When the lid is closed slowly, the compression can be assumed to be isothermal. The gas can be compressed either isothermally or adiabatically from the same initial conditions to the same final volume. Compare, without calculation, the work done in each process. The best thing to do to begin with would be to draw a graph showing those two processes. So I've got my pressure and volume axes to begin with. We now need to draw the adiabatic and isothermal curves. So we want the process to take place between these two volumes. Now I've got my two curves. Let's label those as adiabatic and isothermal. You'll notice we're interested in the work done in each process. So that relates to the area under each graph. Just by looking at this, we can see that the adiabatic expansion is going to have a larger area under its curve, so it's going to have a larger work done. To score the marks for this question, we need to describe what's happening in words. So the first point to make is about the steepness of the curves. And that's going to be your first mark. The next mark will be gained by talking about the area under the graph. So that's your second mark. Your third mark will be for coming to a decision about the work done and which has the higher work done, which in this case is going to be the adiabatic change. And that's your third mark. So 3 marks there. Figure 5 shows the PV diagram for a theoretical petrol engine cycle compared to the indicator diagram for a real 4-stroke petrol engine with the same maximum and minimum volumes. So as stated, we've got figure 5 here with 2 graphs, one for the theoretical cycle and one for the real cycle. Compare the theoretical and real engine cycles. In your answer, you should state and explain the differences between the cycles and explain why the work output per cycle of the real engine is less than that predicted by an analysis of the theoretical cycle. So it would be a good idea for this question to break your answer down into 2 sections, one for the first bullet point and one for the second bullet point. So let's first of all look at some differences. The first thing to say is that on the real cycle on the right, the corners are rounded, whereas on the theoretical cycle, they're more sharp. And the reason for that is that the valves don't open and close in 0 time. They do need a non-zero amount of time to open and close. So that's the first point to make. I'm not going to assign marks to that point because the marking structure isn't as simple, but I'll discuss that at the end. Another thing to note is that there are straight vertical lines on the theoretical cycle, whereas on the real cycle, there are curves. Now, picturing what this means exactly, given the axes we have, if there is a vertical straight line on this sort of graph, it means that the change is occurring at a constant volume. So we're saying that the heating and cooling takes place at a constant volume, which in reality doesn't happen. A constant volume would mean that the piston isn't moving. So for this feature on the theoretical cycle, the piston would have to stop moving. So that's another valid point. Another point to make is about the gas that's taken in the ideal cycle, which we're assuming is an ideal gas, and usually just air. But in the real cycle, there wouldn't be an ideal gas necessarily, and there might also be some exhaust gas or fuel vapor. Now for this statement, it doesn't necessarily rely on the graph, but it's just a stated difference between a theoretical cycle and a real cycle. Let's now move on to the second bullet point. The first thing to say is that the work done in a given cycle is indicated by the area of the loop. So because the real loop is smaller, the work done will be less. So the reason for this difference in work done can be put down to a number of things. The first is that the real cycle will have friction, whereas an ideal cycle ignores this. There are other ways in which energy is lost, as in used up and taken away from the useful energy output, and those are from things like driving oil and water pumps and opening and closing valves. So looking back over this response to the question, you can see that I've made 9 points. Now, according to the mark scheme, that would be enough to get 6 marks, but that's only true if there are plenty of reasons linked to the statements that are made. If fewer than 9 points are covered, then marks will be lost, and the marks will be lost at a higher rate if those points lack reasoning. There's also a mark for quality of written communication. So if your writing isn't legible and the important key terms aren't used, then a mark will be lost there as well. So as is the case with any 6-mark question, it's worth looking at the mark scheme in detail and seeing where the marks can be picked up, because often it will be down to the examiner's judgment on where those marks are allocated. An ideal heat pump and an ideal refrigerator operate between the same hot and cold spaces. Which statement relating to the coefficient of performance, or COP, is correct? Tick the correct answer. Now, the first thing to note here is that the temperature of the hot space is going to be greater than the temperature of the cold space. That's going to come in useful because the way of calculating the COP for a refrigerator is different to the way of calculating the COP for a heat pump. So let's write those two things down. So you can see that the formulae are very similar. However, for the heat pump, the fraction has got TH on the top, whereas for the refrigerator, it's got TC on the top. And you notice, as we said before, TH is greater than TC. So if the denominator of that fraction is going to be the same in either case, then the COP of the heat pump must be greater with any values of TH and TC, provided that TH is bigger than TC. So the answer must be the second one. An ideal refrigerator operates between a cold space at a temperature of -1 degree Celsius and a hot space at a temperature of 70 degrees Celsius. Calculate the input power to the refrigerator if the rate of transfer of energy to the hot space is 100 watts. So the first thing to do is calculate the coefficient of performance of the refrigerator. I'm just going to add some labels there. So let's substitute in some values and find the COP for the refrigerator. So we've substituted in the values there. Bear in mind that those are in Kelvin. And we end up with a value of 3.83. And that doesn't have a unit because in that calculation, in that fraction, we have a temperature on the top and a temperature on the bottom. Now this coefficient of performance of the refrigerator can be put into another equation. So we can look at this in terms of power supplies. So we've got the power taken from the cold region is QC, and then QH is the power supplied to the hot region, which is the 100 watts that were already given. So if we use this to work out the power taken from the cold space, and then the difference between the two will be the input power to the refrigerator. So we ended up with a value of 79.3 watts for the power taken from the cold region. So the difference between the two values is going to be the input power. And that gives us a value of 20.7 watts. Just be careful not to confuse the letter used for the watts, which is a capital W, with the W that we've also used for the input power, because those are different things. So in terms of marks for this question, you'll get your first mark for correctly calculating the coefficient of performance of the refrigerator. Your second mark will be for correctly calculating the power taken from the cold region. And then your third mark will be for correctly calculating the input power. So 3 marks there.